So in this part of the lecture, I'm going to discuss how Fourier transform is applied in quantum mechanics. This will be just the beginning of the story. Fourier transform is extensively used in quantum mechanics, so this is not going to be covered in one lecture. This will come in different stages. So in a previous lecture, we saw that, say, e to the power I kx minus omega t was a solution to the free Schrodinger equation. Remind you what the free Schrodinger equation is. It's free because there's a potential. And also, we are working in one dimension. Otherwise, this would be replaced by the Laplacian operator. Okay, so for the free Schrodinger equation, the particle energy is h bar omega, and it was related to the momentum. So omega is related to the momentum p through the relation which was E is p squared by 2m, and that gives you, when you plug in the Einstein relation and the de Broglie relationships, it gives you a relationship between omega and p. So this is an example of what we call a dispersion relationship. So this is how either the energy or the frequency is related to the wavelength or the wave number. So for the solution, for the plane wave solution that we had here, we could have had a plus sign here that would describe a wave moving to the left. The minus sign gives you a wave moving to the right. You know, it's obvious that the velocity of that wave is given by omega over k, because we follow the phase, the constant phase, you know, that travels at that velocity. So this velocity is actually called the phase velocity. And so this is the phase velocity. And in general, the phase velocity has basically no physical importance. And let me tell you why. Okay, it'll come in stages. So, you know, let's consider instead the Schrodinger equation where there's some potential. So we have I h bar d psi by dt is minus h squared by 2m. Then we have the kinetic terms, and then we have the potential term, right? So, so a general solution to the Schrodinger equation will not be a plane wave, but there will be some kind of plane-like solution, but the dispersion relationship that's coming, say, from this guy because of the presence of this thing, will not be the same dispersion relationship as this thing. It'll be more complicated. So a general solution to the Schrodinger equation can be thought of as a superposition of plane waves or plane wave type of solutions. And we express a general solution, which of course also depends on time, will be given by a Fourier integral over different k modes. So the Fourier integral over psi will be given by different k modes, but now instead of just having kx, this will have a time dependence. So what we have here is we have a bunch of waves which are moving both to the right and the left. The right movers will have k positive. For the left movers, will have k negative, and you know the integral over them, the Fourier integral over them, will give you the time dependent wave function. So the new ingredient here is e to the power minus I omega t. which encodes the phase velocity of the Fourier mode e to the power I kx. And once we specify what the relationship between omega and k is. So if we are to describe by, say, by this guy, some kind of physical particle, then what we expect is a wave which is more or less localized. So a particle, has some localized position in space. So if this wave function is going to describe the particle, then it'll be something like this, right? If it just goes on and on, forever, if it just goes on and on forever, then of course this is not going to be a particle or it'll be a particle whose position is completely not known. But when we're doing experiments and we're sending an electron, we may not know the exact location of the electron, but we know that it's in some small region of space, and if we are going to associate a wave to it, we expect that wave to have some sort of localization like this guy. So such waves are called wave packets. So this is an example of a wave packet. And so the wave, according to this expression, each of these guys is a phase, but this whole thing is a wave packet. So a wave packet consists of many different phases, and all these different phases will have their own phase velocities, but the wave packet itself will move with the same velocity as the particle. So the wave packet will have a different velocity, and that velocity is the physical velocity, and that velocity will be called the group velocity, because it is the velocity of the group of waves. So unlike the phase velocity, the group velocity is actually something physical. So let's discuss group velocity a little bit more. So let's consider a wave packet, and from the discussion of the examples of Fourier analysis, we saw that if a wave packet has a spread in space, which is say delta x, then its spread in in k space is given by something such that the product of these two things is something like 1. We used a different notation before. We used this and that, but it's basically the same thing. So so let's take a wave packet, and then the integral in principle goes from minus infinity to plus infinity. But if it's a wave packet, then the integral over k will be over some finite region, and we can just call that delta k. So, and this is going to be my Fourier coefficients, and I'll have e to the power I kx minus omega t of dk. Now let's suppose that omega varies slowly with k. So omega will have some relationship with k. So omega is a function of k. That is what we mean by dispersion relationship. And that let's assume that omega varies slowly with k. Then we can do a Taylor expansion of omega, which is omega 0. So omega 0 is going to be omega evaluated at, say, some value k naught. So we're expanding it around k naught. So we'll have k minus k naught. And then we'll have d omega by dk, which is evaluated at omega equal to omega naught. And then we'll have higher order terms, which will be k, these kind of terms. So now if I plug this into this expression, then what we're going to get is we're going to get s of t, and then we can factor out this thing. And then we're going to have, so this is a times, not an x, an integral over del k dk e to the power I k minus k naught, and then we have x minus d omega by dk times t. So let's discuss this formula. What this represents is a wave whose wave number is k naught. The wavelength is 1 over k naught, and omega is its omega naught is its frequency, but its amplitude is modulated by this factor. And so we can, if you're graphically representing it, it's something like this, and these wavelengths, this wavelength and the frequency will be given by k naught and omega naught, but but this whole thing is modulated by this, and the velocity of this amplitude is given by d omega by dk. So the velocity of this group of waves, not with just one frequency, is given by v group will be given by this factor d omega by dk, and this is going to be the group velocity, and this is the velocity with which this wave will move forward, and therefore the particle or the energy will also move forward with the group velocity. So the group velocity is the physical velocity. So there's another interpretation to the group velocity, and this is a bit subtle, but consider this wave psi of xt, and it's made out of many plane waves which have different values of k, but outside this wave packet over here, in all these different phases are randomly distributed, and therefore when we sum them over, they give 0 due to destructive interference. Whereas inside this wave packet, what happens is that the phase is stationary. The phase of my wave is stationary, and therefore the phase, they interfere constructively. So what is my phase? Of course, the phase of my wave, the original wave, was kx minus omega t. And if it's stationary with respect to k, that means this is 0. But that also means that this is equals to k minus d omega by dk times t. And this shows that my group velocity, the velocity of the wave, is d omega by dk. So this is another way of thinking about the group velocity as in terms of the stationary phases.